Okay, so we're going to start by looking at some different ways of measuring gases. So it's a way of describing gases and measuring them. And then I'm going to show you how to do some just conversions between various units. So to describe a sample of gas completely, we have to consider 4 variables. So the first variable is the amount of gas. And we measure this amount of gas in our very favorite unit, the mole. So the amount of gas is measured in moles. And we know this already from our stoichiometry unit that 1 mole of gas contains, or 1 mole of anything, contains 6.02 times 10 to the 23 molecules of gas, which is Avogadro's number. We also know from our stoichiometry unit that we can convert between moles of gas and liters of gas, so the molar volume of gas, as long as we're at standard temperature and pressure, is 22 liters per mole, and that's for any gas at STP. So that's one way of measuring gas, and this is one we're already familiar with. The second way is volume. Again, we have a pretty good understanding of what volume means. So volume is symbolized just with the capital V. So a volume just means, you know, basically the 3-dimensional space that the gas occupies. So a gas will fill or fills up a container, right? It spreads out to the entire space that it's given. So the volume of the gas is always equal to the volume of the container that it's in, because a gas particles just continue to spread out. So they just spread until they can't spread anymore. The container kind of traps them. So they will have whatever volume that container has. So when we're measuring volume, we use the liter. Sometimes you'll be given a volume in milliliters, and generally for most calculations, we first convert from milliliters to liters before we do the calculation. Another good equivalency to know is that 1 liter is the same as 1,000 centimeters cubed. So if you look at these, then you could then set cubic centimeters equal to milliliters. They would be equivalent. The third is temperature. And temperature, of course, we know what temperature is, but in the properties of matter unit, there was some reference to the Kelvin scale for temperature. So the Kelvin scale is often what we use, and we'll be using it throughout this gas laws unit. And the Kelvin scale goes from 0 upwards. So there's no negative values in the Kelvin scale. So because we're most familiar with degrees Celsius, it's good to know how to get back and forth between the 2 units. So 0 Kelvin, which is known as absolute 0, which was talked about in the last unit a little bit, absolute 0 is equal to 273 degrees Celsius. So this equivalency is very important because this is how we're going to get between the 2 different types of units. So to convert from Celsius to Kelvin, what you do is you add 273 to the Celsius temperature. So we learned earlier that temperature measures the average kinetic energy. Sometimes we call that KE, kinetic energy. And kinetic energy is just the energy of motion. So when you increase the temperature of something, you increase the amount of motion of the particles. When you decrease the temperature, the particles' motion decreases. So we can think of temperature as a measure of this kinetic energy. So if we want to go between these Celsius temperatures and get them to Kelvin temperatures, what we're going to do is we're going to add 273 to the Celsius temperature, right? So plus 273 each time. So if we do that, negative 210 degrees Celsius, if we add 273, we would get that that is equal to 63 Kelvin. Okay, the 145 add 273 would give us 418 Kelvin, and 2156, if we add 273, would give us 2469. Okay, so of course, if you want to go the other direction from Kelvin to Celsius, you would subtract 273. The thing you should note is that you will never have a negative value for Kelvin temperature. The lowest possible value you can get for Kelvin is 0, okay, absolute 0. So if you end up with a negative value, you've done the wrong operation. Okay, the last one is pressure. Again, we have a pretty good understanding of pressure probably as well, or we definitely have heard of pressure before, so symbolized with P. And it's just a measure of the force per unit area. So where is this force coming from if we're talking about a gas? How do we get pressure? Well, pressure from a gas is caused by the collisions of the gas particles, and they're colliding not only with each other, but they're trapped within the walls of whatever container they're in. So as they move around with their kinetic energy, they're going to bump into the walls of the container. So those collisions with the container walls create a force on those walls, and that force is known as the gas pressure. Okay, so obviously the more particles contained in the space, the more collisions there's going to be with the walls, right? So if you decrease the space that the gas is in, you're going to get more pressure, increase in pressure. So some of these things are, the nice part about this unit is you can kind of envision these things happening, or you have a sort of intuitive understanding of what's going on here. So that kind of, it's very relatable, I think you'll find. So every time a gas molecule hits the wall, it pushes on it, and that exerts a force, and that's what the pressure is. Okay, so let's talk about our atmospheric pressure. So we know the first part of these notes talked about the gases that are found in the atmosphere. So of course these gases can also be measured in all these 4 ways: amount of gas, temperature, pressure, and volume. So if we're talking about, there's something known as atmospheric pressure, and that atmospheric pressure is something you've probably heard in a weather report before. So it's often given in kilopascals. So the gases in the atmosphere also exert pressure on everything they're in contact with. So you kind of think the closer to the surface of the Earth you are, the more gas particles are above you in the atmosphere. So the more gas particles there are above you, the more pressure you're going to feel. Not that we actually feel it, but the higher the pressure is going to be. As you climb higher in the atmosphere, there's fewer particles above, so that lowers the atmospheric pressure. So in the last unit, we talked about the boiling point, and how the boiling point of a substance changes, the boiling point of a liquid changes as the pressure changes. So if you were to boil a pot of water at a higher atmosphere, like up on a mountainside for whatever reason, because the atmospheric pressure is lower, the water will actually boil at a lower temperature. Okay, so that is a little bit related to the last unit. Whoops. Okay, so in weather forecasts, the air pressure gives us a strong indication of what types of, or definitely connects to weather patterns. So you'd hear the atmospheric pressure recorded in kilopascals. And this is shortened to kPa. So that's one possible unit for pressure. The other unit, and this one often in chemistry is used, is something called atmospheres. And atmospheres are shortened to ATM. And there is a third unit we'll talk about in a second, but just to relate these two units, 1 atmosphere is equal to 101.3 kPa, and that is known as the standard atmospheric pressure. So going back to our molar volume of gases, when we're talking about the 22.4 liters per mole of any gas, we talk about STP, standard temperature and pressure. Well, the pressure component, this is the standard atmospheric pressure, that's the 1 ATM or 101.3 kPa. There's a third unit for measuring pressure, and that one's called millimeters of mercury. So mm for millimeters, and Hg is the symbol, chemical symbol for mercury. So the reason this unit exists is because this corresponds to the rise of mercury in millimeters up a closed tube. So at one point, atmospheric pressure was measured like this. You'd have mercury in this tube, and the atmospheric pressure pushing down would push the mercury up the tube. And you could actually measure how far up the tube the mercury got pushed in millimeters. So how do we get between these 3 units? That's what we're going to spend the next little bit of time doing, is we need to know how they all relate. So we already know that 1 atmosphere is 101.3 kPa, and to relate to millimeters of mercury, this is also equal to 760 millimeters of mercury. So all 3 of these are equivalent, and this is all of the pressure units at standard atmospheric pressure. So let's do some conversions to get between these units, and we're going to use our favorite process, dimensional analysis. So here is one example. Convert 203 kPa to atmospheres. So I simply start with the unit I'm given, 203 kPa, and I set up my fraction for dimensional analysis. I'm going to put the unit I want to cancel on the bottom and the unit I want to get to on the top. To get between these two, I just use these values. How do these 2 units relate to each other? Well, 1 atmosphere is equal to 101.3 kPa. So my kPa cancels, and it's 203 divided by 101.3. So that actually gives me 2, whoops, why isn't that working? ATM, there we go. Okay, so a very simple calculation to get there. Let's try a few more. This one says convert 2.4 atmospheres to kPa. Okay, so this time we're going the other way. So 2.4 atmospheres, and we're going to go to kPa. So I'm going to put atmospheres down here, kPa up here. We know that in 1 atmosphere, we have 101.325 kPa. Okay, so atmospheres cancel, and I'm just multiplying 2.4 by 101.325. and that gives me 243.18. Always make sure, that's kind of messy. You put your units in. All right, now we've got a millimeters of mercury to atmospheres. So let's put our 450 millimeters of mercury. So millimeters of mercury down here, atmospheres up here. And if we look back at our equivalencies, 1 atmosphere is 760 millimeters of mercury. So I'm going to divide by 760 to get 0.59 atmospheres. All right, couple more to go, and then you can work on the assignment. It's assignment 2. I skipped over assignment 1. Just due to the fact we're not in the classroom. I normally assign a graphing assignment for the concentration of carbon dioxide in the atmosphere, but I decided to skip it and go into the second assignment, which is just practicing with these conversions. So I don't think you'll have any difficulty with it. So 4.1 atmospheres, and we want to get 2 millimeters of mercury. So atmospheres here, mmHg here, 760 in 1 atmosphere. So I'm multiplying by 760, and that gets me to 3,116. Good, and finally, this is the one that's a little bit different. When you go from millimeters of mercury to kPa, it's still the same process, it's just you don't end up with a 1 in your fraction, but that's okay. So 2,150 millimeters of mercury. Whoops, I'm getting a little messy here. Millimeters of mercury on the bottom, kPa on the top, and if you look back, it's 101.325 kilopascals is equal to 760 millimeters of mercury. So you're actually doing 2 processes here. You're multiplying by the 101.325 and then dividing by the 760. So it's sort of got 2 steps. So when you do that, you would get 286.64 kPa. All right, so you guys can go ahead and try some of these on your own on worksheet 2.